What if I told you that the secret behind all modern electronics lies in purposefully contaminating pure materials? Sounds weird, right? Let's break down how doping turns an ordinary material into tech powerhouse. So the doping is the process of adding impurities to a pure semiconductor to change its electrical property. Because the pure semiconductor has some limitations as such limited conductivity. So there are basically two types of semiconductors. One is intrinsic semiconductor and another one is extrinsic semiconductor. If you take in the case of intrinsic semiconductor, it means a pure semiconductor material like silicon or germanium with no impurities. This is the key. And if you take in case of extrinsic semiconductor, we say if it's doped with particular material, then we say it's an extrinsic semiconductor, and these are of two types. One is N-type and another one is P-type. If they're doped with extra electrons, we say it's N-type, and if it's doped with extra holes, then we say it is P-type. The common examples for P-type and N-type are boron, aluminum, boron, phosphorus, and arsenic when they're doped with silicon or germanium. So right now we have just seen what is extrinsic semiconductor and intrinsic semiconductor. In case of intrinsic semiconductor, there is no external doping. If you see, only 14 group elements are bonded within themselves together to form intrinsic semiconductor. In extrinsic semiconductor, if you see in the middle, we are having an atom which is having 5 electrons in its valence shell, and it is bonded with 14 group elements which are having 4 valence electrons, and we get one extra electron which doesn't participate in bonding, and this extra electron is the reason for conduction. And there are two types as we have already discussed in N type. One is N type and another one is P type. So if you see in case of N type, there is an extra electron because an extra electron is present in the atom which is having 5 valence electrons. If you take in case of p type, one electron is lacking in the atom which is bonded with this silicon. So because of this thing, it forms a hole here, and this hole is responsible for conduction in p type, and this extra electron is responsible for conduction in n type. By now we know that electrons are responsible for conduction in n-type materials and holes are responsible in p-type materials. We know what an electron is. Electron is a subatomic particle. But we don't know what does this hole even mean. So before we dive into what is hole, we have seen in last video something known as valence band and conduction band. So here we are having conduction band and here we are having valence band. So let's suppose the electrons are there here very tightly closely bound and electrons in conduction band are loosely bound to each other. So the energy difference between valence band and conduction band is known as band gap, which is denoted by the letter Eg. So when an electron gains sufficient energy, which is equal to band gap, it moves from valence band to conduction band. But this dear electron, it doesn't normally leave. It leaves with a hole here. So let's look closely what actually happens in the valence band when it is leaving holes here. So let's suppose there are 4 spots here, and there are 3 people occupying these spots. And due to sudden change in their mood, they want to shift to this direction. So how do they do it? First, the person which is sitting next to this empty spots, he comes here. So he occupies this position and leaving an empty spot here, and the rest 2 positions are same. And this guy is waiting for his turn to move. So now we have seen that there is an empty spot beside him. So he tries to occupy this empty spot. So this person sitting here, he'll remain the same, and this person will occupy this empty spot, and this place will become vacant now, and the last person remains the same. So, and this person also eventually moves to this empty spots and fills it. So something like this. Now the empty spot is at the end. So in the same way, the electrons also move like this when there is hole. So there is hole here, right? This is hole. So let's suppose we are giving electric field in this direction. So let's suppose the electrons are moving in this direction. So let's zoom in and see how this movement takes place. So the electron which is present beside the hole occupies this empty spot, and we get a hole here, and the rest of the electrons remains the same. Now again the electrons are moving in this direction. So now the electrons which is present here will remain the same, and this person, the electrons is this empty spot and occupies this position. So again, the electrons are moving in this direction. Let's suppose then this electron occupies this empty spot and fills it, leaving the hole to come here. So from this we can see that the electrons are moving in this direction and the holes are moving in this direction. So from this we can see that holes can be treated as positive charged particles, even though they are not real charged particles. But due to this thing, these can be treated as positively charged particles. Definition of Fermi level says that the probability of finding an electron is 50%. It's nothing but an energy level again. Yeah, so when we're talking about this electron, here we are not talking about the electron which is in paired state. We are talking about electron which is free electron, which can move and which can conduct electricity. So in we know that in N-type, electrons are major charge carriers, and in P-type, holes are major charge carriers. You might be wondering, we are saying here holes are major charge carriers, and there are no electrons here. So how are they even conducting? So in the previous slide, we have seen what is what. So holes are just an empty spot, but still there is an electron movement. There are free electrons because of holes. So that's how the conduction in P takes place here. So if you talk about Fermi level, it's like something like, for suppose you're lost somewhere in a huge unfamiliar city. You're wandering around searching for a sign that tells you you're close to home. The moment you see your city's nameplate, you feel relieved. You know you're in a familiar territory. In the same way, the Fermi level is that sign. It tells us how close we are to the free electrons that can conduct electricity. If it's near the conduction band, we know electrons are ready to move. If it's near the valence band, holes are dominating. It's like an ultimate guide to semiconductors' electrical behavior. About an intrinsic semiconductor, there are equal number of holes and electrons in intrinsic semiconductor. So this is conduction band, which is the energy level is denoted by E suffix C, and this is valence band, which is denoted by letter E suffix V. And the Fermi level is somewhere in between, not somewhere, but exactly in between conduction band and valence band. This is denoted by letter EI, which is also known as intrinsic Fermi level of semiconductor. So this literally means that we can find free electrons in the conduction band as well as in the valence band. And if you talk about N-type material, so N-type, so here we are having conduction band, here we are having valence band, right? So here we are having intrinsic Fermi level, which is nothing but Fermi level before doping it. So after we dope with N-type material, the Fermi level shifts to this side. So this means that near the conduction band, there are more free electrons which can conduct. So this is what it literally means. If you see in case of P-type material, so this is conduction band and this is valence band, and this is intrinsic Fermi level. It is again nothing but the Fermi level before doping anything. So here we will have Fermi level. because the conduction is taking place in valence band itself. Because there are a lot of holes in the valence band, and these holes are responsible for movement of electrons in valence band. So that's why we can say that Fermi level is close to valence band in p-type material, and Fermi level is close to conduction band in n-type material. So we know that there are some extra electrons in the lattice itself. So the extra electrons are very loosely bound to the atom. So at room temperature itself, it goes to conduction band. So that's why this Fermi level is staying near the conduction band. But if you take in case of p-type material, there are no such things. We are in fact having holes in the valence band. So because of this, the electrons even can't move, and instead electrons just move themselves in the valence band. Well, we know holes are responsible for conduction in p-type materials and electrons are responsible in n-type materials. So the letter N denotes the electron concentration and the letter P denotes hole concentration. In an intrinsic semiconductor, the hole concentration in the electron concentration is equal, and that can be denoted by letter Ni, which is equilibrium carrier concentration. So according to this law of mass action, it states that the product of number of electrons into the number of holes is always constant, and that is equal to Ni square. So in n-type material, the number of electrons are more compared to the holes, and in p-type material, the number of holes are more compared to the electrons. So if you take in case of intrinsic semiconductor, the number of holes and the number of electrons are equal. But whenever we are doping n-type material into a normal intrinsic semiconductor, the whole concentration is decreasing compared to the normal concentration which we are having in the intrinsic semiconductor. This is happening because of a process known as recombination. If we see recombination in terms of n-type material, so let's suppose we are having a conduction band here and we are having valence band here. We are having way too many excess electrons. So there are excess electrons in the conduction band which are free to move, and we have holes here in the valence band. So the electrons which are present in the conduction band, they loses energy and comes to the least energy state, which is valence band. Again, why do this electron do this? I mean, like, electron gains some energy and goes to conduction band, right? So why is it again coming back? Because of the stability reasons. Whenever the energy is more, the stability is less. So in order to gain stability, the electron tend to lose some energy and come back to the previous state. So the electron which is present initially there is now coming back to this valence band and occupying this position. So if you see here, the number of holes are decreasing in n-type material when we are doping with excess electrons. This is not just happening in the n-type material, this is happening in p-type material also. So we are having conduction band here and valence band here, and having excess holes in valence band and electrons in conduction band. So these electron number is constant if we are comparing it with the intrinsic semiconductor. So it is having equal number of electrons as they were in the case of intrinsic semiconductor. But because of this recombination process, the electron from conduction band moves to the valence band. So it occupies this position, and we have conduction band here. And the electrons, if you're talking with respect to intrinsic semiconductor, they're decreasing. So that's why in p-type material, the holes are more and the electrons are less. So the law of mass action, which is holding true for intrinsic semiconductor, is also holding true for extrinsic semiconductor. So this number of electrons into number of holes is always constant. So we are trying to increase the holes. Then the electron decrease. If we try to increase electrons, the holes decrease. This is what we have seen. And this law of mass action is holding true for this. So this will become to Ni square. So this Ni is intrinsic carrier concentration and it is constant for any given semiconductor at given conditions. Summarize today's topic. So we have talked about semiconductor. There are two types of semiconductors. One is intrinsic semiconductor and another one is extrinsic semiconductors. In extrinsic semiconductors, there are two types of semiconductors. Okay, one is P-type semiconductor and another one is N-type semiconductor. In P-type semiconductor, holes are the major charge carriers. In N-type semiconductors, electrons are the major charge carriers. And then we have moved our discussion to Fermi level. So for pure intrinsic semiconductor, the Fermi level lies exactly between valence band and the conduction band. And for N-type material, it is close to conduction band, and for P-type material, it is close to valence band. So the Fermi level diagrams for intrinsic semiconductor and N-type and P-type materials are shown here. So it is exactly in between the valence band and the conduction band for intrinsic semiconductor. In case of N-type material, it is close to conduction band, and in case of P-type material, it is close to valence band. Then we have more discussion to law of mass action. It states that the product of hole concentration and electron concentration is always constant, and that is equal to Ni square, which is equilibrium carrier concentration, and it holds true for both intrinsic and extrinsic semiconductors.